Hi, this is Dr. S, and this is video 7 in my series on reaction rates for Year 12 A-level chemistry. In this video, we'll look at the Boltzmann distribution, or as you might have seen it, the distribution of molecular energies. So what that means is, what is the link between the energies of molecules and how many molecules have that energy? This is a graph. Okay, so this is how the graph looks. So you have energy on the x-axis and the number of molecules on the y-axis. Now what we should hopefully know is that there's a variety of energies that any particular molecule have. If you have a sample of gas, for example, some particles will be moving really fast with lots of energy, some particles will be moving slowly. But what we know is that there will be no particles that have zero energy. It's not possible to completely stop a particle or a molecule. So as I'm drawing this graph, it's going to start at the origin. We also know that the vast majority of molecules or particles have an average energy, but there'll be some that have very high energy. So this is how the graph ends up looking. Starts at the origin, has a hump in the middle where the majority of particles lie, and then there are some that have very high energy. Now we don't know exactly what the maximum energy would be, so it never touches the x-axis again. It tends towards it, but it never actually touches it. So it's really important when you're drawing one of these, which is a really common exam question, is that you start at the origin and never touch the x-axis again with the hump in the middle. Now what we can imagine is, whereabouts is the average here? Well, if we're talking about the modal average, then the most particles are here, aren't they? But that is different to the mean average. I'll put the mode average on. But that is different to the mean, because if you look at where the modal average is, you can clearly see that there are the number of particles, which is the area under the peak, is smaller on the left hand side than it is on the right hand side due to this tail. So the fact that there are some molecules with very high energy changes the mean average, so it's higher than the modal average. So the mean average would probably be about here. Okay, now something else that's often put on Boltzmann distributions is then the activation energy of a reaction. So let's say that's here. Now there are no units or scale necessarily on this. It's a sketch graph, so it doesn't really matter where the activation energy goes. But let's use it here for an example. Remember, the activation energy is the minimum energy required to start a reaction. What that means is these particles here that have the energy greater than the activation energy, so the shaded area, will be the ones that are able to react. The molecules have energy greater than the activation energy, so it means it can overcome the activation energy barrier and create a successful or effective collision. You can see that the vast majority of particles do not have enough energy to react. It's only, in this case, a small amount of particles that react. That does not mean that these are not bumping into each other, but they're not bumping into each other with enough energy to kickstart the reaction. Okay, so this is a really important skill because they are often asked in exam questions. In my next video, we'll look at how the Boltzmann distribution can be used to explain why a catalyst increases the rate of reaction. I'll see you then.